Okay, Assalamualaikum. Afternoon. Okay. Any more coming in? Right. So today, again, we will continue with what I was with our lectures with the rest of the topics. The things that I've already discussed with Dr. Nizam is that we'll be skipping one particular chapter on this series, chapter 7. Okay, so we'll chapter 6, and then we skip chapter 7, and we're going to go straight to chapter 8. And in chapter 8, probably we will not cover everything, but at least the essential parts that you need for mostly of the physics course. Okay, so let me start. So today we're going to do slightly different, which I wanted to avoid in the beginning, because it's always, for me, it's always good to have your own set of notes. But since I don't have any at the moment, so I have some scribbles and that's about it. So let me use the book directly at the moment. So again, please allow me to do so. Today we're looking at the case of chapter 6, vector analysis. So most of this you have been introduced in chapter 3, or if I'm not mistaken, on linear algebra. So the idea of vectors, we have already seen it before, the form of vector space and so on and so forth. Here are just some applications. The first section, section 2 here is essentially about vector multiplication. Are you seeing this book? Somebody, please respond. Anyone? Okay,
Yes,
good.
Doctor.
Okay, great. So I hope you can see my scribble here then. So here, let me just mention this. There are two perspectives. I've already mentioned this also in the other lectures. So the first is essentially your algebraic perspective. Okay, so these are normally written in terms of components. Okay, and one advantage. Okay, there's always an advantage and a disadvantage of particular perspective. The advantage of the algebraic way is that you can do calculations easier. Okay, we'll get to what I'm trying to say in a minute. So the other one is geometric. Okay, over here is the in terms when you describe vectors, it describe vectors in terms of magnitudes and angles. And what is the advantage of this particular perspective is that it's good for I have to be careful not to write too fast. It's good for visualization. So so let's look at this particular product in vectors. So this is the scalar product or the dot product. So the ones that you have almost used for your calculations are this, and this is essentially algebraic. Okay, and this is what I call mostly geometric. And in fact, if you have seen this before, you know that the product is talking about projection there. Okay, so you project a particular vector B, say, along a vector A. Okay, and then essentially this scalar product gives you this magnitude, product of magnitudes times cos theta. So it's cos theta is projecting along A there. Similarly, for your scalar product, product or cross product, so you have the usual way, or there is another notation I've already introduced, but probably not introduced in the other class, is this component form. This carries from the what you call the algebraic perspective. For cross product, the component form, or the index notation, is of this nature. If you want to have a look, please look back into the notes. So this is AJBK, or the full vector itself. Then it will be an epsilon ijk ei, the unit vector along the ith direction, AJBK. So again, these are good for calculations, but again, to essentially see what's going on, you probably need to draw something like this. This is again telling you about the geometry thing. Okay, so you have your A cross B. The angle is between this A and B, but where's the direction? The direction has to be perpendicular to both A and B. So you will point out, so if A and B forms a so-called plane, then C will be orthogonal to the plane. Okay? So these are kind of things that perhaps hidden when you write in terms of components, then otherwise if you do geometry, you can actually see it. Okay, so where are the so-called dot products and vector products appear in physics? Here is the case of work done. So these are normally done in terms of the force times displacement. In the simplest sense, here assume that the displacement is actually along the direction of the force. Okay, but generally one could have that your force will be pointing in a different direction. So here's a picture of the force pointing in a different direction. So, but the displacement is actually along the horizontal direction. So in order to calculate what the work done is in this particular case, would be a dot product. Okay, or it could be in an infinitesimal sense, where your force is acting on a particular path. Okay, so in this particular case, then you have the differential of the work done is given by F dot dr. Okay, are you seeing the cursor, the white cursor moving? Somebody? Anyone? Do you see this cursor?
No, I don't.
Okay. So okay, let me just in this sense I will have to actually show where I'm pointing at. So this is where you have the differential thing. So you can think of this. If I need to displace this amount of distance, so I will need to do an integration of f dot dr, which we will do in the later sections. Okay, so let's try to move faster. So here is another idea of that you see in mechanics. You talk about the torque. I'm not sure what they use as a symbol for torque. but I normally use this as I think I did the wrong order. Go to Z. Torque is given by R cross F. Okay. So again, over here, the standard example will be this so-called lever kind of problem, where you know that if you exert force at the end, then you will be able to see this thing sort of rotates. Okay, so that's in the simplest sense, and then the distance that's going to be considered in that particular case is that horizontal distance, which is perpendicular to the action of the force. Okay, so we can do this much more generally. You can talk about, okay, let's have something which has this particular distance over here, and then you exert a force in that direction. Okay, since you're not seeing my cursor, so here's the position that you're exerting a force. Okay, so the force is along that. Okay, the 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 position vector is actually having this direction over here. Okay, so when you exert this force, it will cause again a torque, which is going to be perpendicular to both your R and F here. Okay, another name for torque, okay, is essentially a moment of force. Okay, let me jump ahead. So, do I need to say anything about that? Okay, I think those are things should be familiar to you in somewhere in a high school or pre-university kind of education. So here is another one, angular velocity. Let me try to, angular velocity, and over here you can actually see that you have this formula that you have seen before, and that sort of tells us about here the rotations in a particular plane here, and then your R over here, well, how should I do this? This is okay. Essentially here, your origin of the coordinates somewhere here, and then the position vector is pointing there here, and then your velocity that you're supposed to find out is actually the tangential velocity here. But the omega over here, normally you think of this as a circular kind of motion here. So physically you actually define your the one that you actually measure is essentially your velocity. Okay, but you know the rotation axis is going to be there. Okay, so this is essentially giving you the rotation axis, and that gives you the vector omega here. Okay, so in this particular case, this v is what we call the linear velocity, and omega is your angular velocity. And because of this cross product, then you can see the magnitude is essentially r omega sine theta. Where the sine theta comes from is from here. Okay, so theta is coming from down from the origin there to r here. So the radius of the circle here is essentially r sine theta, not just r. Okay. So if you want to get back to the usual what you call formula that you have seen before, then you really want to project it down on this xy plane. Then sine theta will be sine pi over 2, okay, and that will give you v equals to r omega. So that gives you the circle down below. Right. What else do I need to show here? Oh, the other thing, this is again, no, it's not quite apparent when you write down the formula. Okay, even in this geometric form, you are just giving the magnitude. So how do you actually determine this omega pointing above, or it could have been pointing downwards? Well, this is essentially what we have, the right hand rule. So you have this, going this direction. I'm not sure you can see this right hand thing. Okay. So right. Again, these are just convention. Okay. So you need to be aware these are not is fixed by no, only historically. So it's not something defined in a natural way. What else? Okay, triple products. Okay, we have seen before that no, if you have a parallelogram, then you can actually define what are what are the vectors that sort of builds up the parallelogram. Then the area will be given by in this case it's C cross B or B cross C in this case. So that will give you the area. Then if you really want to do a three-dimensional version of this is what we call a parallel pipette. Okay. And that means there'll be a some vector here, so it defines the other dimension of the sides of the parallel pipette, and that to get the whole volume, then you just need this vector multiply with this base, okay, in this triple product sense. So this gives you the volume. Again, I'm not sure whether how much of this have you been exposed to, but no, I'm just going through these ideas quickly. So the triple product, you have seen it in this particular form, this determinant form, or you can use it in terms of the index notation. So index notation will be AI epsilon I j k b j c k. Okay. So you can look up my notes to have a look. So there's another triple product which is coming from the cross product. Excuse me. My throat is a bit dry. Well, again, this gives you this back gap rule, so I'm not going to do this again. But one of the things that again, this requires a little bit of imagination, is the fact that, let me just check my phone notes. Okay, it's the fact that when you do this, remember the parallel pipette thing. Okay, so you have your B cross C there. So if I do another vector, so gives you the what you call another vector. In this case, okay, let me just draw it. It will be another vector here, so perpendicular to both well, I should not do that. Control Z. So okay, B cross C will be some vector in this direction, for example. Okay, or actually C cross B here. So this is C cross B. So if I want to find another vector which is perpendicular to this, what do? I do a cross product. So I can do a cross product in this way. Then this vector, okay, this, I should not do that. This vector will be perpendicular to both A and B, sorry, will be perpendicular to C cross B. So since we are doing this in 3 dimensions, the only way that this can be what you call placed is this vector has to be in this plane of B and C. Okay, so that's why if you look at what is the answer that you get in this A cross B cross C is some value here, and then proportional to B, and then some value here proportional to C. So it's a linear combination of B and C. So in other words, it has to lie somewhere on this particular plane. Okay. Right. What else? Again, another example of a triple cross product is the idea of this is again of a torque, but instead of about the axis, but perpendicular axis. This is about a line. Okay. So as you can see, this is not quite perpendicular. If it's perpendicular, then it has to be perpendicular to R, but no, it's slanting in this manner. So one could again find what the expression for that. Then this is just simply n dot what was it? N dot R cross F. I think it's somewhere below here. Let me just check. Well, okay, no. So in other words, if it's along this line, and this line is in the direction of n, then the torque will be there. So this is just a generalization of your previously defined torque. Okay. So what else? Oh, okay. Another good thing to know is the decomposition of your vectors. Okay. Sometimes over here you would like to decompose, say like that picture just now. You have this line n defined by the vector n. So one could essentially decompose your vector r into components which are parallel. So this is the parallel component here, and then the other one is the perpendicular component. So one could always do that to any vectors, including this force, for example. Okay, so when you do R cross F, okay, when you do R cross F, then you'll be able to see that, okay, you can just simply expand this. This will be 0, for example, it's a parallel component. This is not necessarily parallel because you have to remember the perpendicular vectors are no, since it's in 3 dimensions, there you will see that no, your two vectors are perpendicular and f perpendicular might not be parallel, okay, because you have extra degree of freedom there, or extra directions. So this is not 0, but this is 0, okay. And then again, one could also use the fact that what was it? The vector, where was it? The vector. Let's take this vector for example. Okay. R perpendicular across F parallel. Now F parallel will be in the direction of, this would be parallel to N. So R perpendicular across F parallel will have to be a vector which is perpendicular to N and perpendicular to R perpendicular. Okay. So it will be in a plane, this will be in a plane perpendicular to N Z. So when I do the following, so I take the dot product of this with N, dot product of that, this term will disappear, this term will be disappear, and what's left is this quantity. Okay? Right. So the numerical examples, I'll let you read it for yourself. The other, here's a good example of a different kind of example that use a different kind of application. Okay, so here is an application towards coordinate transformation. Okay, where you're going from, say, x, y, z, your ordinary Cartesian coordinates, to some new coordinates given by u, v, and w. And what do? You define these vectors. So your A here is a change of the position vector. What's the position vector? This is the vector R along U. And this would be the same thing, okay, along V. This would be the same thing along W. And remember that U, V, and W could be in different kind of direction with of your x, y, z. Okay, so what happens in this particular case, you see that when you define these vectors A, B, and C in this way, let me go down, then your Jacobian is essentially coming from that triple scalar product. Okay, because your components over here are given by derivatives. Okay, so this gives you all these rows. So this is A, this is B, and this is C. So when you do the determinant for this is equivalent to this A dot B cross C. Okay, remember that your this is the same like before. Ax, Ay is z, Bx, By, Bz, Cx, Cy, Cz. Okay, that's equals to that. Right. Okay, let's do this one. Okay, so this is just the case of the application of triple vector product. So if you have, for example, your angular momentum is defined by r cross p, okay, and p equals to mv, okay. But then you have seen that before, that v equals to what, omega cross r, or what is it? I never memorized this. Yeah, omega cross r. So then what happens in this particular case, you plug in v into there, and then you get your angular momentum as a triple vector product, r cross m omega cross r. Okay. Another one would be this centripetal acceleration. We will look at this in a minute in a simpler case. It's again a triple vector product between omega cross omega. Where is this coming from really? This is like omega cross r is cross v there. Okay. Right. Okay. So let's move to the next section. Okay, now so far we have not done any kind of, apart from the change of coordinates just now, we have not done any kind of calculus with respect to vectors. So now we are introducing that. Okay, so here one could think of, say, a vector given by these components ax, ay, az, where each of these component is going to be a function of t, for example. Okay, so what happens in this particular case, one could then define what we call the derivative of the vector. Okay, so here's the derivative of vector, which is simply defined as the derivative of the components, and then you add up their respective directions over here. One has to be careful over here. Here your I, j, and k are called constant unit vectors. If for some reason these are not constant, what's going to happen? So you have dA dt equals to d dt of I ax plus j ay plus k az. So just looking at the first term here, okay, if I want to differentiate that, then this would really imply, no, you need to use the product rule. So I need to differentiate I with respect to t, leaving ax, okay, this part over here, and then you have to differentiate ax, leaving I, okay, and you have that. So if your I and j and k are not constant, then you would have this extraneous terms. But since I and j and k are constants, okay, so this will be equal to 0. Why is it constant? Well, your x, y, z axis stay fixed. Okay, so your I, here, your j here are just fixed vectors. Now compare this, later on we'll look at it. Compare this with the case, say, now let's do a simpler case. Here, okay, in this case, this is x, y, and this will be your constant vector I, constant vector j. But I could have done this in a different sense if I use a polar coordinate. So here would be your unit vector along the radius or the r, and then this would be unit vector along, say, theta here. So theta is here. So in this particular case, if you change the position of your position vector, okay, then your unit vectors of ER and E theta changes as well. So in other words, in this particular case, these are not constant vectors. So one has to be careful when you differentiate a vector. You need to be to make sure what are the unit vectors involved. If the unit vectors are coming from your x, y, z coordinate, then they are essentially constant, and you can just simplify it to this. But if it's not, then you need to do more differentiation. Okay. So I think that should be enough. With vectors, you still have to remember that you can do a lot of different other operations. You can have a scalar here multiplied to the vector A, and then if you do a differentiation, then you have to differentiate your scalar as well, and then leave A, and then leave the scalar, and then differentiate the vector. Okay, so this is again like your chain rule, product rule, sorry. This is like your product rule applied to vectors. Similarly, for the case of the products of vectors, okay, generally it's vectors, okay, because here is a scalar times vector, okay. Here is a vector times a vector in terms of a scalar product. You still have the same idea, okay. So you have the product rule intact. Similarly, for the case of the cross product, only in the case of the cross product, one thing has to be the order of A and B on both sides of the equation, okay, should be maintained. So if it's A appears before B here, then when you do the differentiation, then your whatever involves A has to appear whatever that involves the vector B. Okay, so that's the only caution that you need to take into account. Okay, let's look at some nice examples here. So here is the case of a motion of particle at constant speed. So what does it mean? If it's a circle, then your dot product of your position vector, okay, which gives you r squared here, should be a constant, okay, because it gives you the radius of the circle, radius square of the circle. Okay, and it has to be constant, otherwise it will not be a circle. Otherwise it might be an ellipse or something. Okay, so this is constant. Now and then it says constant speed, that means v dot v gives you the magnitude square of your vector v, that will be a constant. So what one can do with these two equations is to take the differentiation of the whole equation. So essentially this is the application of that. Okay, so you do that, so you find that you get let's do the steps here. So you have r dot dr dt plus dr dt to r, but these two things are no since a dot b equals to b dot a, then this simplifies to that. Okay, these are just the same thing. Okay, so you get oops, what am I doing here? Are you still seeing this? Okay. So again, the same thing happens when you differentiate your v squared. So you get your v dot again v dot dv dt. Dv dt is your acceleration here. Dr dt is your velocity. Okay. So you get r dot v equals 0 for the first one, v dot a equals 0 for the second one. And what does it imply there? The first one will imply that your r is perpendicular to v, and then the second one will imply v will be perpendicular to a. Okay. And from the second equation, or the first equation, okay, from the first equation here, you can again differentiate that. Okay, differentiate r dot v equals 0, then you get r dot a plus v dot v equals 0 here. Or you can rearrange this, and this is r dot a equals to minus v squared. Okay, here again we have this idea that, okay, remember that r is perpendicular to v, and a is what was it? Sorry, just forgotten. Your a is perpendicular to v. So both vectors are perpendicular to each other, so that means that your r and a has to be either parallel, okay, meaning r and a points in the same direction, or r and a is antiparallel. Okay. So in other words, the angle between the r and a, remember that this is r a cos theta. So we need to find out what is this angle. The angle should be either 0 or 180 degrees, okay, or pi radians. But since the answer is actually negative, okay, so it cannot be 0, because that gives you 1. Okay, so what we need is a negative answer, so we need a cos 180 degrees. So once you do that, then you can actually identify this with your earlier equation here, and your cos theta is minus 1. Okay, and then you can rearrange this, and you get what we have seen before, which is the centripetal acceleration. Okay, right. Okay, here is another thing that one needs to also learn about. We already mentioned just now that you can have unit vectors along your polar coordinates. So here is ER. Okay, so ER, if you just look at how this triangle is being drawn, okay, so this is a unit vector over here, and then you have this component, the vertical here, and here is your horizontal here. So you remember that vertical over hypotenuse, this is cool stuff. This gives you your cos theta, sorry, sine theta. I can't remember my school things. Sine theta, and then adjacent over hypotenuse gives you cos theta. So this is by construction now. Okay, so I know now that this is essentially sine theta here, and this is actually cos theta here, because your hypotenuse is of unit length, so you get cos theta there and sine theta there. So now your ER, which is in that direction, is this vector, okay, this vector plus this vector to give you that vector. Okay, so ER is essentially I cos theta plus J sine theta. Now one could also try to do theta is actually moving in this direction. Okay, so that means your unit vector E theta will also move in that direction. Okay, so one could also construct the same kind of thing using some similar triangles, and then you'll be able to show this. Or the easiest way to think about this is to think of your ER and E theta, which should be what you call perpendicular to each other. So if I want something which is perpendicular to each other, so I will need E theta dot ER to be equal to 0. So the combination that give you that scalar product to be equal to 0 is just this combination. Okay. Right. So finally, again, as I mentioned just now, your ER and E theta will change if you change the position of your position vector. So you can see that in this particular case, if you take the derivative of your ER or E theta, you would get a non-zero answer. So here is DER dt by using chain rule essentially. Then you get your E theta times D theta dt, and for your E theta, the time derivative is essentially minus ER d theta dt. Now you know what d theta dt is. Essentially this is omega, your angular velocity. Okay. So okay, I think this is just an example. You can read this for yourself. So in other words, you can have your vector A decomposed in terms of I and J, but you can also decompose it in terms of ER and E theta, and that would give you, essentially what you need to be defining your what you call your components AR and A theta. Okay, I will not go into that. So let me see what's next. Okay, so next thing we'll go into a different section on fields, but I think let's take a little bit of a break over here. So Is that all right? Okay, everyone's back. Suppose so. So let me just continue. So before we go into the applications of vector calculus in physics, one needs to introduce the idea of fields. You more or less have come across them in some manner or another. An example of field is essentially like, say, a scalar field in this particular case is the temperature inside a room. Okay, so you might consider the temperature sort of varying inside the room, but you can define a temperature at a particular region of the room. So here's, so I can define, say, over here as T1, here T2, and this will be depending on this coordinates x1, y1, z1 here, x2, y2, z2 here. So they could be different temperatures, but depending on where you are in the particular room. Okay, so having said that, your T over here is just given by a numerical value, a single numerical value. So these are essentially scalars. Okay, so in other words, a scalar is now has been defined at all points of the space. So that defines what we call a scalar field. Okay. Besides scalar field, one could also define, instead of just numerical values at these points, one could have some idea of vectors. So these are things that you have come across perhaps much more commonly in electromagnetism, to talk about electric field. Okay? So you put a point charge at a particular region of space, the electric field will push that point charge, or the test charge they call it, in certain direction depending on how the electric field behaves. Okay, so these are examples of what we call the vector field, because your electric field is given by a vector which has three different components: Ex, Ey, Ez. And if it's defined in all the points in space, then it's a field. Okay, and we call that a vector field. So that should be enough for the introduction. Oh, okay. So this is the scalar field here. This is the vector field that we just defined just now. One of the other things one could have is the idea of potentials, equipotentials, or sometimes called contours, which are going to be useful, or there will be application of vector calculus with respect to this. Okay, the equipotentials are the cases where you have maybe it's better to think in terms of contours. You probably have seen maps before where you draw a particular, say, contours over here that shows you, say, the height of a particular hill, for example. Okay, so one could have something like this. Okay, so these are contours according to height. And then one of the things that we know, if you are if you do hill climbing, you would like to find the easiest way to climb the hill, right? According to height. So in which direction will you find the easiest way to climb the hill? Then you find that this would probably the best direction here, because the spacing between the contours are much more broad compared to over here, where this is probably the steepest. Okay, so we will be looking into those kind of what you call problems with vector calculus. So the first thing that we want to know is, for example, is the idea of a directional derivative. Okay, so one of the example just now was to look at temperatures. So just like the contours of the hill, you might want to see where the temperature is varying very fast or where the temperature is varying very slow. So if you want to do an experiment, for example, you would like to find a place that almost the temperature is not varying at all, so that you have a control experiment, perfectly controllable environment, okay, so that your temperature is not fluctuating inside that particular room. So these are things that are going to be of useful. So in this particular case, the derivative, usually we think of derivative with respect to a particular direction. Okay? Say dt dx, or dt dy, or dt dz. So these are fixed direction. These derivatives are with respect to fixed directions of x, y, and z. But why are we limited to that? Okay, you can imagine like the contour just now that I've drawn. One could have any direction at all. Okay, so in other words, this direction is not along x or y, for example. Okay, so you would like to find a directional derivative, particularly if you have a parameter that parameterize the temperature. So here the parameter is given as ds here. Well, you can think of what ds is supposed to be is the distance that you have seen before. Okay, so this is something that's being used to define a parameter that sort of dictates how the temperature varies. Okay, so now you want to do this in an arbitrary sense. So over here, I can consider any line. So if you remember how a line is actually defined in terms of a parameter, it's given by r equals to r naught plus some specified direction here. What should I use? Okay, let's use the same thing. Specified direction u times the parameter s. Okay, so this is r naught is just a given point. Okay, so then what one does is to write down your components here, just like this. Okay, your u is given by a, b, c, and one could simply differentiate this equation. trying to do, I'm going to push this. Differentiate this equation and essentially get the directions A, B, C here. But this is just your components of your what you call position. Usually what we want is something like your temperature just now. That depends on your position rather than the position itself. Okay. So in this case, we want to know what's the directional derivative along this direction u. So that would be given by this chain rule here. Okay, so you can think of your t just now, it's given by phi here. So you have d phi ds equals to a chain rule d phi dx ds. When I said d for the first one was the partial, okay? Partial phi, partial y, dy ds, partial phi, partial z, dz ds. So, and your dx ds and dy ds, dz ds has been given by your components of your vector u. Okay. But what is this? You can think of, okay, I've seen this before. This is just A is just the x component of your u multiplied by the derivative of your phi with respect to x here. Okay. So, and then the corresponding components of each. So this is essentially del phi, which I will define in a minute, dot product with u. What is del phi? Del phi, I think it's on the next page. Del phi is given by this vector. The derivative of that scalar field phi with respect to each coordinates. So this is now what we call the directional derivative. Your del phi here dotted with your direction of interest. Okay. So one can start now. Okay, I want to find out, say, here's an example, just a simple example first. Find the directional derivative of this scalar field given in terms of this function, okay, at the point of 1, 2, minus 1 in the direction of that. Okay, so over here your vector A is giving you the direction, but it's not normalized here. This is not normalized. So to make it normalized, we take it divide by the length of this. So the length of A is simply square root 4 plus 4 plus 1, and that gives you 3. So you divide it by that length, and that gives you your u. Okay. Calculating your del phi or gradient phi, okay, and that gives you this vector here. And then if we want to evaluate at a particular point which is given here, then you just substitute your x, y, z over here, okay, and then you get this quantity here. Okay. So now what you do is to dot product this with your direction, and that will give you the derivative, directional derivative d phi dx at the point 1, 2, minus 1 in the direction of u. Okay, and this is given by phi terms. Okay, so one could essentially do other cases, and this tells us, okay, how steep is that particular function phi with respect to the distance. So you know, okay, if you go along certain points in a certain direction, okay, there will be a steep point or much more what's the opposite of steep? I can't remember now. Much more flat kind of thing. Okay. But if you take your geometric pictures now, define the as being given by del phi dot u. Okay. Remember, we have our geometric picture that this is given by the magnitude of del phi, and u is actually u is a unit vector here, and then what's left is the cosine of the angle between u and your gradient phi. So here's a picture over here. So here's the vector u here, and here is a gradient phi, and this is your angle theta in between. So that will now be given by that. Okay. Now you can almost immediately see, in order to get you the largest value, you need to make your cos theta to be 1. Okay, because cos theta is between positive 1 and minus 1, right? So if you want to make it the largest, then you take theta equals to what you call, what is it, 0, right? And we want to make the most negative, then it will be theta equals to pi. Okay. So in this particular case, keep reaching to my, I don't, okay, never mind. So in this particular case, the rate of your, no, the largest rate of, here it says the largest rate of decrease is when you have the negative sign, when you theta equals to phi, and the largest rate of, I think, increase should be the largest value d phi ds is when theta equals 0. Okay. So the example given here is about the temperature again. So you can have a look at that. I'm going to skip this. Now, what I want to do is consider now the idea of these contours that we had earlier. Okay, contours. How do we define contours? Is to fix your phi at a constant value, at a certain height, for example, or a certain temperature. Okay, so in this particular case, if you fix this to be constant, when you take your gradient of phi, this should be equal to 0. Okay, so in other words, in this particular case, what does that say? That simply says del phi dot vector u just now, okay, equals 0. I'm trying to see here. Give me a minute. Missing a particular point here. Right. Okay. The point I wanted to make is to say that del phi is going to be yeah. The thing that I wanted to make is your del phi is going to be proportional to the idea of a normal to the surface. Now I'm trying to get the right way to approach this. Uh, Yeah, I suppose I have to go through this kind of picture here. So your u will be somehow sort of parallel to your tangent. Okay, so your u parallel to the tangent, then essentially your normal will be sort of perpendicular to that u. Okay. Yeah, okay. So I missed that. So in fact, over here it's been stated. Yeah, your u is tangent to the surface phi equals to constant. In other words, this is not just arbitrary u. Okay, your u is given as tangent to the surface. Then your gradient phi over here, because of this, your gradient phi will be, since u is a tangent, then this will be a normal. Okay. So I think that's the main thing that I want to say. So in other words, one could always find, given a particular surface, for example, over here now, let's look at this example. Here you have a surface given by this product of x cubed y squared z equals to a constant. So now one could try to ask, okay, what is the normal to this? Well, the normal to this is to think of this as a function. Okay, so here's the function here, and take the gradient of that, and the gradient of that is given by this vector here. And if you are given the point, then you can plug in the values of x, y, z. Okay, given as 1, minus 2, and 3 here, so you get your numerical values over here. So now what we know now is that your gradient w is essentially in the direction of the normal to this particular surface. Okay? But remember, this is at times you need to normalize it, at times you do not need to normalize it. So in this particular case, it doesn't seem to be using the normalization. So the question here is the equation of the tangent plane and the normal line here. So the normal line is already found to be, well, the normal vector is already found to be your 36i minus 12j plus 4k. So let me go down. I'm keeping my attention somewhere else. Okay, sorry about that. So the equation of the line should be given by this. Okay, this is again, remember, this is coming from this is okay. This is a tangent plane. The tangent plane, if you look back into the notes on geometry of planes and lines, this is given by n dot r minus r naught equals 0. So this is equation of a plane. And then the line, okay, the line should have, remember this, well, okay, the direction is going to be given by the things below here. Okay, so these are the components of the direction. And then on top is essentially your r minus r naught. Okay. I'm trying to remember what's the thing. R minus r naught. Yeah, okay, it's the same thing as this. R minus r naught equals to some vector here times a parameter t or s. Let me use s back again. US. So this is a parameterized equation of a line. But now your line is supposed to be the normal. So here I'm replacing your u by your n, and n is given by this thing. This is the simplified version of that. Okay, so your n will now have your components 9 minus 3 and 1 here. And how do we get this equation? Remember, the components has to be proportional to s. So if you divide this, okay, it's a bit difficult for me to, okay, maybe I do this in terms of components here. So if I take the x component of r minus r naught, say I write it as component 1, then this will be proportional equals to u1s. Then the same thing with r minus r naught 2. This will be equal to u2s, and so on and so forth. So when you divide this by u1, for example, r minus r naught 1 divided by u1, this will give you s, but s also can be given by r minus r naught 2 divided by u2, and the same thing, r minus r naught 3 divided by u3. Okay, so this is if you can still remember how you define equation of the line inside chapter 3, I'm not mistaken. Okay, so that will give you the equation of the normal. So your u here will now be replaced by that normal. Okay, let me see what's next. Okay, this is going to be a bit more difficult. So your gradient just now, okay, was defined in terms of ijk. But we are not limited only to this. Now, one could essentially have this your xyz be replaced by some other coordinates, like your, say in this case it's given in terms of cylindrical coordinates, so that means your coordinates are r, theta and z. The only problem is that how to replace your I, j and k here. There will be some quantities that's going to have some kind of what you call modifying factor. Let's just consider there is another way of but since I think that would be probably need a little bit more maths than what you see over here. Okay, but the easiest way to think about this is to think of, okay, what's the dimension of the FDR? Okay, so here if you just take your DDR alone, the dimension of this is 1 over L. Okay, so if you consider d d theta, this has no dimension, or this is a dimension radian, okay, which is really dimensionless. Okay, so one would seem to have made an addition of two different quantities with different dimensions. So that means one needs to actually modify this term so that it has the dimension of 1 over length. And the required factor there was given by this 1 over R. So there is a much more natural way of deriving this, which I will not have the time to explain over here. But in any case, you are supposed to know this, especially for the standard coordinates, cylindrical coordinates, and spherical coordinates. But I know, sometimes it's difficult to remember all things. I don't memorize them, so I look it up. But it's okay in your test if you need to use your gradient in terms of cylindrical coordinates. You are allowed to look at the book because you have an open book exam. Okay, so you don't need to memorize it, but you need to know how to differentiate. Okay, I think that's probably the thing that I want to say. Okay, so here again the same thing happens. Okay, so here is 1 over R, here again is 1 over R. Same thing happens for the spherical coordinates over here, but it's now much more complicated. Okay, you have a factor of 1 over R sine theta, R sine phi. So in other words, there must be a better way of deriving this. I could show this at some other point, but not at this juncture in time. Okay, let us try to see what's next. Okay, I think probably this will be the last thing that I want to say today. So your gradient is what we call an operator. So just like your derivatives, okay, it's an operator. What does it do? It operates on a function, say, to give another function. Okay, let's say, let's give a symbol, say g. So this function g is coming from the operator acting on your function f. Okay, so if one has more operators like the ones involving in the gradient, then this is supplemented by these directions here. Then we call this as a vector operator. So a vector operator, that means what can be done with a vector operator? Well, we have the various ways of doing a product between vectors. Okay, one is like, one thing is like your scalar multiplication. So this here you have done this. So vector with a scalar multiplication. Let's consider this. So a times v, for example, okay, is a scalar multiplication. But now, since what you want to do, this is now an operator, and you want to add it on a scalar. So the ordering is slightly different. So the ordering here becomes gradient of phi. Okay, so that is the one that we have seen. Okay, the gradient of a scalar function. But you could also have something like gradient dotted product with a vector function, okay, which is given here, for example. So this defines what we call the divergence of V. Okay, so divergence of V is that, and then you could also have the divergence, the curl of V, which is taking the gradient cross product of V, okay, which is shown below here. Now, both of these has some physical meaning. Okay, your divergence is related to how this will be made more clearer when you do integral theorems. How your vector field is actually pointing at a particular point from in a region of space. Okay, for example, over here, if the vectors are defined in this way at this point, okay, then you see that your divergence of V will not be equals to 0. Okay, and the curl of V is something that talks about rotation. For example, if you find that your vector field is pointing in this kind of direction, so denoting some kind of rotation there, then your curl of V will not be equals to 0. So you have some physical idea of what this divergence and curl is supposed to mean in some particular context. Okay, so I will. Is there anything more? And of course, once you have the gradient of phi, for example, then I can think of this as a vector V. So I can now take a divergence of V, and this is just divergence of a divergence of a gradient, and this is denoted as del squared. Okay, del squared is what we call the Laplacian, and the Laplacian appears in physics in many different ways, which is mentioned over here. So I probably want to stop there for today. Again, here is in terms of the different coordinate systems. It's going to be very difficult to remember all of this, but again, as I said, the important thing is not to memorize but to know how to use it. Okay, so I think we'll stop there for today and probably continue in the next lecture, and we'll continue with the line integrals and then all the other integral theorems that we are supposed to do in the next lecture, hopefully. So that means we're more or less about to finish this particular chapter by the next lecture, but we'll miss out the chapter on the differential equation. So for the differential equations, what I will probably do is to do some recorded lectures. For differential equation, it's not too much of a concept, but no, it's much more calculation, for differential equations. Let me also mention that hopefully by tomorrow I will get your SCL modules out, and you're supposed to do this in groups of 4. I know that you're already in the final week, so the submission should be sometime in the study week. Okay. For submission. So I will upload this later on. I'm just trying to get the various materials for the modules. Okay. So that's it for today. I hope you don't get too confused by the no. I'm trying to cover a lot of things today, so that it might go a bit fast than before. So let me go back to you and let me download attendance. I hope this works. Okay, I'm having the same problem like this morning. So can you message me your attendance for today in the WhatsApp? Okay, so I think we'll stop for today at this point. Okay, thank you everyone.
Thank you, Doctor.
Thank you, Doctor.
Okay, remember to give me your attendance. Okay. Okay, bye.